In mathematics problems, we frequently have to expand powers of binomial terms. A binomial is an expression like x plus y, where we have two variables added together. And so we might need to compute x plus y to the power 6 or x plus y to the power 7. And the question is, how can we do this easily? Now, we can certainly expand these expressions in the usual way, but it becomes rather tedious when the powers become large. So, for example, x plus y squared is x plus y times x plus y, which we can expand using crab clause to give us x squared plus 2xy plus y squared. And x plus y cubed is x plus y times x plus y squared, and we already know that x plus y squared is this expression, so x plus y cubed becomes x plus y times x squared plus 2xy plus y squared. And that, if we expand by crab clause, gives us this expression, x cubed plus 3x squared y plus 3xy squared plus y cubed. We can expand x plus y to the 4 similarly by noting that x plus y to the 4 is x plus y times x plus y cubed, which is x plus y times our previous expression for x plus y cubed, and we can expand x plus y times all of that to give us this expression. Now, this rapidly becomes tedious, and even at x plus y to the power 4, there's an awful lot of work to do. For higher powers, it becomes very tricky indeed. We need a better method, and the better method comes from the place it usually comes from in mathematics problems, and that is noticing patterns. To look for patterns, we'll consider the expansion of x plus y cubed, which we can write as x plus y times x plus y squared. Now, I've rewritten this as 1x plus 1y times 1x squared plus 2xy plus 1y squared, i.e. I've put in the coefficients explicitly even where they don't appear in the original expression, so I've put in the 1s, and I've put them in because we're particularly interested in where the coefficients come from. This will make it easier to see. The terms from this expansion fall into two groups. The first comes from multiplication by 1x, and I've written all of those on this line. The second comes from multiplication by 1y, and I've written all of those on this line. Let's look at terms of the form x squared y. There are two of them. This one is produced when we multiply 1x and 2xy. This one is produced when we multiply 1y and 1x squared. And when we gather like terms, the coefficient of x squared y will be the sum of those two coefficients, 2 plus 1. And we should note that 2 plus 1 is the sum of the coefficient of the term with the power of x to the 1, i.e. this thing here, and the 1 is the coefficient of the term with the power of x being 2, i.e. this one here. Now, this is a pattern that in fact continues, as we shall see. Here, I've written out one above the other the expansions for x plus y to the 1, x plus y to the 2, x plus y to the 3, and x plus y to the 4, and we will be able to see how the patterns arise more easily when we do this. As you can see, I've also written out the 1 coefficients explicitly. Let's first look at the terms in the expansion for x plus y cubed. Where does the coefficient 3 for x squared y come from? Well, it comes from the multiplication of x and 2xy and the multiplication of y and 1x squared. So we sum those two coefficients to produce the 3. Where does the coefficient of 3 come from in front of xy squared? Well, that comes from the multiplication of x and 1y squared and the multiplication of y and 2xy. And so we sum the coefficient 2 and the coefficient 1. Now let's look at the expansion of x plus y to the 4. How do we get terms of the form x cubed y? Well, we get one of those terms when we multiply x by 3x squared y. We get another one of those terms when we multiply y by 1x cubed. So to get the coefficient 4, we add the 1 from 1x cubed and the 3 from 3x squared y. How do we get terms of the form x squared y squared? Well, we get those by multiplying x by 3xy squared and by multiplying y by 3x squared y. So the 6 comes from adding the coefficient 3 from 3x squared y and 3 from 3xy squared. How do we get terms of the form xy cubed? We get 1 when we multiply x by 1y cubed. We get another when we multiply y by 3xy squared. So the coefficient 4 comes from adding the coefficient 3 from 3xy squared and the coefficient 1 from 1y cubed. And now it's clear how we generate the coefficient of any term in any line. If we want the coefficient 6, we add the 3 from here and the 3 from here, i.e. from the two terms in the previous line to the left and to the right. If we want the coefficient 4, we add the 3 and the 1 from the terms to the left and the right in the previous line. This also works for the expansion of x plus y squared, which I haven't yet looked at. The 2 here comes from adding the coefficient from the terms to the left and the right in the previous line. And we should note that the coefficients of the terms at the end of each line are 1. We should now be able to generate correctly the coefficients in the expansion of x plus y to the power 5. So we need a 1 at the beginning and end of the line, and then we need to sum adjacent terms to give 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5. And we can also produce just as easily the coefficients in the expansion of x plus y to the 6. However, we're not quite done with these expansions because even though we can find the coefficients easily now, we have to decide what are going to be the powers of x and y to go with those coefficients. So we're going to have terms of the form x to the something times y to the something associated with each of those coefficients, and we need to see the pattern that generates those. We can find the pattern for the powers by looking at the expansions of x plus y squared and x plus y cubed. I've written x plus y squared as x plus y times x plus y, and if we expand this using crab claws or FOIL, we get x times x, x times y times x, y times y, and because of the way that we multiply the brackets out, each term comprises exactly 2 elements, 2 x's, an x and a y, or 2 y's. We can simplify the whole thing into 1 times x squared times y to the 0 plus 2 times x to the 1 times y to the 1 plus 1 times x to the 0 times y squared. And we can see in each case that if we add together the powers in each term, we get 2. 2 plus 0, 1 plus 1, 0 plus 2. If we look at the expansion for x plus y cubed, we multiply x plus y into x plus y squared, which I'm going to write as xx plus xy plus xy plus yy. And now we note that each term is multiplied by either an x or by a y. Because of this, we end up with exactly 3 elements in each term in the final expression, xxx, xxy, and so on. And there is some combination of x and y in each element. And the simplified form of this becomes 1x cubed times y to the 0 plus 3x squared times y to the 1 plus 3x to the 1 y squared plus 1x to the 0 y cubed. And again, we notice that the powers in each term sum in this case to 3. And we note that the 3 is precisely the power by which we are expanding. And in the previous example, the 2 was precisely the power by which we are expanding. And we can also note that as we move this way along the terms, the power of x decreases and the power of y increases. But in every term, they always sum to 3. Now we have everything we need to expand x plus y to the power n for any value of n. First of all, we have the coefficients, which I've laid out here in this triangular form, which goes by the name of Pascal's triangle, and those coefficients are formed as we saw earlier. Secondly, we have a rule for the powers of each term in the expansion of x plus y to the power n. The kth term in a line looks like a coefficient, which I will call nck, times x to a power n minus k times y to the power k, and k runs from 0 to n. nck is the kth coefficient in the nth row of Pascal's triangle. Now suppose we're expanding x plus y to the power 4 and we want the term where k equals 1. Well, n will be 4 because the power is 4, and so the term we are interested in looks like 4c1 as the coefficient times x to the power 4 minus 1 times y to the power 1, and the coefficient is in the line marked 4, and k varies from 0 to 4. So we have to go to the element where k is 1, which is 4. So this expression becomes 4c1, which is simply 4, times x to the 4 minus 1, which is 3, times y to the 1, which of course simplifies to 4x cubed y. And it's worth pointing out the lines that correspond to n equals 0 and n equal 1 indicate the coefficients in the power of x plus y to the power 1, which is simply x plus y, or 1x, 1y, and x plus y to the power 0. And of course, any real number to the power 0 is 1, so we simply have a bare 1 as a coefficient. And now, using Pascal's triangle and the rule for the powers, we can expand something like x plus y to the 5 mechanically. We take these coefficients from the line numbered 5, and we insert the appropriate powers, x to the 5, y to the 0, x to the 5 minus 1, y to the 1, and so on. And note, in each term, the powers add to 5. And that finally simplifies to x to the 5 plus 5x to the 4y plus 10x cubed y squared, 10x squared y cubed plus 5xy to the 4 plus y to the 5. And it's no more difficult to expand x plus y to the power 6 now. First of all, we need the coefficients for n equals 6, but we get those from the coefficients for n equals 5 by the left and right addition process. So we have 1 plus 5 is 6, 5 plus 10 is 15, 10 plus 10 is 20, and so on. And then we expand by using the coefficients and the rule for the powers to get x to the 6, which is 1x to the 6, y to the 0, plus 6x to the 5y, which is 6x to the 5y to the 1. And again, you can see that the powers always add to 6. And that pattern continues along the terms where we are taking the coefficients one by one in turn.